So we're going to finish up section 5.4. Okay, looking at the second part. The only drawing we're going to do today is when we get to a word problem. Just sketching will be helpful. Other than that, we're going to try to do a lot of things with numbers today, like adding and subtracting vectors without making a sketch. Okay, just doing arithmetic. So, first thing I'm going to explain is what it means for two vectors to be equal to each other. Okay? What does it mean for two vectors to be equal? So, suppose that we had these two vectors, v and w. Those two vectors would be equal. Does anyone have a guess? What do you think? Yeah?
Like what they are.
Yeah, like what would have to happen in order for v equals w to be a true statement?
Well, same value.
What would have to be the same value?
The or
What about the vectors would have to be the same?
there.
Yeah, each variable. The x's would have to be the same. So these are called your horizontal components, and these are your vertical components. So the vertical and the horizontal components would have to be the same. So as an example, let me sketch two vectors that are the same. So like this. Start here and go there. Start here and go there. Those two vectors are the same. Two vectors being the same doesn't mean they start from the same point and end at the same point. It means that if you were to measure the horizontal, which in this one is 2, and in this one is 2, and if you were to measure the vertical, which in this one is 4, and that one is also 4, they match. Horizontals and the verticals are exactly the same. That's what it means for two vectors to be equal. Any question on that? Okay, some people think they mean it has to be drawn in the same spot. No, they don't have to be in the same spot. All right, so the next thing we're going to look at is the final notation that we can use to write vectors. We've done the brackets, which you guys did in the homework last night, and sketching. I'm going to show you the final notation, which is called unit vector notation. Yesterday, I think towards the end, we talked about what a unit vector was. Somebody remind me, what does that mean? Something is a unit vector? Yeah.
Is it right?
More specific, what about it? If it's called a unit vector, it's something special about it. Yeah?
It equals 1.
What equals 1?
Magnitude.
Yes, magnitude. So if you have a vector that's a length of 1, then that means it's a unit vector. So I'm going to show you guys two special unit vectors. First vector is called I. So I is a special name that we use for a vector. You can't use I for anything else. It's like using this Greek letter. You can't use that Greek letter for anything you want in math. It already means 3.14. You can't change that. Same with I. I means something special. What I means is it's a unit vector that points to the right. So it's a vector that's 1 unit long and it points to the right. There's a picture of I right there. It's 1 unit long and it points to the right. That's all. That's I. The other special vector is J. So again, J is a special name for a vector. You are not allowed to use the J if you want to draw your own vector. Pick a name other than I or J. And you don't know this yet, but don't pick K either. Pick any other letter you want besides I, J, and K. And J is a unit vector that points up. So it's 1 unit long, and it points up. Here's a picture of J. It's 1 unit long, points up. So what we're going to do is we're going to basically take those two little vectors and think of them as like building blocks. We're going to stack them together to make vectors. Okay? And by stacking them together and building a vector out of little i's and j's, that's going to give us our final notation for how we can write vectors. Think of I and j as like building blocks that we're going to use to make a bigger vector. So those are going to be our two, like Lego pieces. Those are the two pieces we have, and that's what we can stack together. So I want to build the vector 3, 4. Doesn't matter where you put it. Just put it anywhere. Just wherever you start, go 3 right and 4 up from there. So 1, 2, 3, 1, 2, 3, 4. All right. So my goal is to build that vector out of i's and j's. I'll change the color so maybe it's a little easier to see when stacking it. All right, let's start with the i's. Those are the ones in red. How many i's am I going to need to link together to start to get me from the initial point to the terminal point? Yep. Let's check. 1, 2, 3, 4. Yeah, we're going to need 3. Right? So that's the first thing I'll do. I'll take 3 of the i's and I'll put them together. Right. That's a little off, but it's because they're so small. It's hard to kind of control on the smartboard. So we go 1, 2, 3. I plus another I plus another I. What's I plus I plus I? Yep. 3i. So 3i. That's the first part. Now I got to figure out how many j's I would have to stack together. How many of the j's am I going to need to get from where I'm at right now to the terminal point? Yep. I need 4 of them. Right, so I'll just make some copies of this. I zoom in a little. It might give me make it a little bigger, easier to see. Okay, so let's see if I can stack those together. So we got 1, 2, 3, and 4. Good enough. So a j plus a j plus a j plus a j. How many j's is that? 4 of them. And I added them onto the end of the 3i. So 3i plus 4j. And that is called unit vector notation. That's it. 3, 4 with the angle brackets, our book calls that algebraic notation. 3i plus 4j is unit vector notation. We'll use both of them, right? But this one is probably more common. Any questions on that? So now, what direction did I point? I pointed which way? Right. Right. And j pointed up. So that allows us to go right and up anywhere we want. But not every single vector you draw goes right and up. If you think this is a vector, look at that one right there. That one goes down and right. So instead of going up and right, how could I go down and left or up and left? Or what would I have to do to the I and the j? Yeah. Yeah, make it negative. Right? So if I is positive, you can go right. If I is negative, you can go left. If j is positive, you can go up. If j is negative, you can go down. That covers every direction you'd ever have to go. Now, what if you had to go like this? From here to there. What would you have to do in that case? Yeah.
Just I.
Yeah, you just need i's. You wouldn't need any j's. But how many i's would you need? Yeah, 3.5, and that's fine. You can have fractions of I. So you can move half I pretend like, scale it. That's fine. You could go 3.7i if you needed to. You can do whatever you want. So you can go in between grid lines, and you can go any direction you want. So you can do anything you want. The only thing you can't do is 3D. Like if you wanted to come off the board. Can't do that yet. I and j only allow you to move left and right and up and down. K is going to be the vector that would be in 3D. That would allow you to come off the board or go into the board. Positive, negative. Any questions on that? Okay. So we're going to look at doing some of the same things we did yesterday. Adding, subtracting, and scaling vectors. But you're not going to draw it. Okay, we're just going to do arithmetic. So, in order to be able to do this, I'm going to give you two vectors. The vectors are going to be called v and w. And alpha is a scalar. Remember, a scalar is just a number. And when we scale a vector, one of three things can happen. Anyone remember, what are the three things that can happen when you scale a vector? Yeah? Yep, shorter, longer. One more thing. Yep. Well, that's longer. Yeah, so longer, shorter, or it could flip direction if the scalar was what kind of number? Negative. Right? So, first thing we're going to look at is how we would add those two vectors up. So vector v, and in a real problem, these would be numbers like that. That's what a problem would look like. But just generically, v would have an x and a y component, and w would have another x and y component. They don't have to be the same. Like I have a 2 and a 3, and then in the other one, a 3 and a -4. They're not both the same. So x and a y in each vector. And if you want to add these vectors up, the old way to do it is you draw v, and you put w on the end, and then you draw your diagonal, connecting the beginning to the end. Well, to kind of get away from the drawing, all we have to do is take the horizontal part of the first vector, take the horizontal part of the second vector, and combine them, add them up. Take the vertical part of v, take the vertical part of w, and add those up. And that's it. And that's the formula for adding two vectors. Now, what do you think would change in this formula? Instead of v plus w, how about, Amber, how about v minus w?
It would just be x1 minus x2 and y1.
That'd be it. Now, the order there is important because when you're subtracting, think about 2 minus 3, 3 minus 2. It's not the same. So the order is important, and it's subtraction. The horizontal component from the first vector minus the horizontal from the second. The vertical from the first minus the vertical from the second. Okay, so that's subtraction. Right, scalar product. Scalar product is kind of like a distributive property. Like if you wanted to take a vector and triple its length. Well, if you triple the length of a vector, what you're really doing is you'd be tripling the horizontal component and tripling the vertical component. And that would triple the whole thing. So like this vector, if you tripled its length, the new vector would be 3, 6. Triple the horizontal, triple the vertical. So it's like you're distributing what you're scaling it by to each number. And all of these formulas, we're going to look at them all again when we do 3D, but they're all pretty much exactly the same, just with another comma at the end. And like for v plus w, you'd have z1 plus z2. You just have one more step after the comma when you do it in 3D. Other than that, it all stays the same. Same basic pattern. Okay. And the last operation, we've talked about this symbol. We've never done any calculation with it. What do the double bars mean?
Absolute value. Oh, no, wait, magnitude.
Magnitude. Okay? And magnitude means length. So if I had a, I don't know if I already drew one on the other page. Yeah, let's just look at this one in black. It's perfect. If I wanted to find the length of that vector in black, it's kind of hard because it's on a diagonal. But how long is the bottom side in that triangle? 3. How about the height? 4. How could you find the length of the vector 3, 4 with that information? Well, that would give you like an equation of the line, if it was a line. But we're just looking for the length of that black side. That black side, if you view it in that picture, that black arrow is really the what? It's the hypotenuse in that triangle. So we're trying to find the length of a hypotenuse. How do we do that? We use the Pythagorean Theorem. Right? So finding the length of a vector, all you have to do is take the first component and square it, take the second component, square it, add them up and take the square root. 3 squared plus 4 squared, and then take the square root. That's the Pythagorean Theorem. And that's exactly what this formula says right here. Right here. The square root of the x component squared plus the y component squared. Notice both of these only require a single vector to do the problem. If you want to do addition, you need 2 things to do addition. You need 2 vectors. You can't add a vector to nothing. So you need 2. You can't subtract a vector from nothing. You need 2. Scale a vector, you only need 1. Find the length of a vector, you only need 1. So let's go through, we'll do one of each. So there is the vectors we're going to be working with, written in both unit vector and the other notation. And we'll practice writing our answer in unit vector and the other notation. We'll do both. I want to start with v plus w. And I don't want to draw. I'm not looking for a sketch. That's what you did last night. I'm looking for just numeric. So, Brandon, if you look at vector v, what's the horizontal component of v? Three is the vertical. 2, yeah. 2, so 2 is the horizontal in v. CJ, what's the horizontal in w?
2.
Alright, let's go back over I and j for a second. I is a unit vector that points 1 unit to the right. So I is your horizontal. J has to do with up and down. J is your vertical. So when you look at I and j, the number in front of I is always horizontal, the left and the right. Okay. Number in front of j is always your up and down. That's your vertical. So if we go back here, the horizontal in V is 2. The horizontal in W is 3 because it's the number with the I. So yeah, when you add them up, we get 5. So the new horizontal in the final answer is 5i. And then the vertical in V is 3. The vertical in W is -4. And we're adding them. So what would be the final answer when I do 3j plus -4j?
Good.
Okay.
Hey.
Hey?
Oh, okay.
Hey. I don't know. I lost it. Yes?
Minus j.
Minus j. 3j plus -4j. It's like 3 minus 4. It's minus j. Now, she didn't say minus 1j. She could have, right? But minus j minus 1j is the same thing. Now, what would that be the same as writing if you did it with the brackets? What would go inside there? Yep. 5, -1. Both notations are correct. Which one will you see on the test? Probably both. But it's really not that hard. If you can write one, you can write the other. Right, so that's adding two vectors. Now, subtracting. If we were doing this the way we did it yesterday, we'd have to take W, flip it around, put it on the end of V, and then all that stuff. We're just subtracting numbers. That's all we're doing. Horizontal minus horizontal. Vertical minus vertical. And those are your two numbers. So let's start with the horizontal. What would be the horizontal component when we subtract? We do V minus W. Yep.
Oh, wait, V minus. Wait. Oh, no, I see what you're asking. -1.
-1. 2i minus 3i. -1. And I'm just going to write -i. You could put -1i, but I'm just going to do -i. All right. And how about the vertical? Be careful with the vertical. Just be careful.
7J.
7j. It's 3j minus 4j. Plus 7j. Or -1/7. Same thing. Either answer is correct. Right. 3v. This is an operation that doesn't require w at all. So forget about w. All you're doing is taking vector v and scaling it. You're tripling the length. So what would vector v come out to if you triple it? Yeah.
6r.
Yeah, I told you to think of that as like a distributive property. Just multiply each component by what you're scaling it by. So 6i plus 9j. Yeah, I'm not going to write it the other way this time, but if you wanted to, it would be the brackets and then 6, 9 in the brackets. Okay, and the last one. The magnitude of v. Okay, so we just said that when you want to find the magnitude, you're really using what theorem?
Pythagorean.
Yep, you're really just using the Pythagorean Theorem. What you are finding is the hypotenuse of a triangle. What are the sides? The sides are the two numbers they tell you. So for vector v, we have a 2 and a 3. Just fill in 2 and a 3 in those two spots, and you're good. So it's going to be the square root of 2 squared plus 3 squared. Did that in the last class too. Because the next number is a 3. 2 squared plus 3 squared, which is going to give me the square root of how much? Square root of 13. Now, if you could simplify it, you would. Like if it was the square root of 20, that would simplify to 2 square roots of 5. Same rules we always use. But 13 is prime, so it doesn't simplify. Okay. Any question on add, subtract, scale, or find the magnitude? Okay. So, last thing before we get into our word problem applications, and there's only 2. So once we finish this, there's 2 questions left. But the word problems take a little bit. Okay. Remember, if the magnitude of a vector is 1, that's called a unit vector. Okay? So U is kind of another special letter they use with vectors to mean unit vector. So if you have to pick a name for a vector, don't use I, don't use J, don't use K, don't use U. You can pretty much use anything else you want. I, J, K, and U are kind of special. All right. So what we're going to be looking at here is we're going to be given a vector, and then I'm going to want you to scale it to force it to be 1 unit long. Don't change the direction. Just like imagine this vector in black. Pretend like it's too long. The vector in red is 1 unit long. I would want you to scale this vector in black down smaller so it becomes 1 unit long. Okay. So we have to see how do we do that in general. So let's say we had, let's say, length of vector. We're going to make a table, and hopefully you'll kind of see a pattern. I'm going to give you the length of a vector, and then I want to know what to scale by to make it 1 unit long. What to scale it by to make it 1 unit long. All right. So let's say we had a vector that had a length of 5. What would you scale the vector by to make it a length of 1?
1/5.
1/5. Yep. Again, I'm not really interested in specifically what you'd scale it by. I'm more interested that you start to notice a pattern of what you scale it by. What if you had a vector that was 8 units long? What would you scale it by to shrink it down to 1 unit? Yeah. 1/8. Now, what if you had a vector that was half a unit long? What would you scale it by to make it 1 unit? This vector is too small. It's different. You got to make it bigger. Yep. 2. So does anybody see the connection between the number in the left column and the number in the right column?
Flip it.
You flip it, exactly. So if you tell me the length of a vector and I scale it by the reciprocal of that length, it will force it to come out to 1 unit, always. 5, 1/5, 8, 1/8, 2, 1/2, 12, 1/12. Whatever number I have, I flip it and multiply it, and that will shrink it down to 1 unit. Or expand it to 1 unit. It depends. If it's too big, it would make it smaller. If it's too small, it would make it bigger. But we're forcing the length to be 1. That's all we're doing. So, this is just what we're doing. I just told you that. So, we're finding a new vector. We're not changing the direction. We're just forcing it to be 1 unit long. What's important is how we do that. Okay, and that's the formula. It's going to be right here. So, the formula for the unit vector, we just said, take the vector that you're given, let's call it vector v, and multiply by 1 over its length. So if your vector was 5 units long, you'd multiply by 1 over 5. If it was 8 units long, 1 over 8. But you take your vector and you multiply by 1 over its length. Now, if you want to think of that as a fraction, you can always put what number underneath something to make it a fraction? 1. So if you want to think of putting those fractions together, you can, just like that. 1 times v is v. And then the magnitude of v times 1 is just the magnitude of v. So this is exactly the same thing I wrote right there. It's just squishing it all together in 1 fraction instead of keeping it as 2. The important thing is the magnitude of the vector is in the bottom. Okay. And if you do that, you will create a unit vector. So in a problem like this, the very first thing you have to do is find the length of the vector they give you. That's step 1. Find the length of the vector they give you. Step 2, scale your vector by the reciprocal of that. That means flip it, put it in the bottom. All right, let's try an example. So, I want to find a unit vector for this. Now, the vector I'm giving you is 3i minus 4j. not sure if is anyone still copying?
Yeah. No.
If you're going to copy a formula, I mean either one, the one that's in the box or the one that I wrote over here, they're the same. If you're going to do that one, I would just do it like that. They're the same. All right. So what did I say step one is to finding a unit vector? That's the first thing you have to do with the vector they give you. Yeah?
You have to find the magnitude?
You have to find the magnitude. How do you find the magnitude? Just did that. It's the Pythagorean Theorem. So, let's find the magnitude of V. It's going to be the square root of, and then somebody fill in for me what goes under the square root.
Three squared minus 4 squared?
3 squared. Careful, what operation do we do with Pythagorean Theorem under the root?
Oh, plus.
Plus. 3 squared plus negative 4 squared. And Matthias, if I do that out, it's going to give me the square root of... Well, start out, what's 3 squared? 9. And what's negative 4 squared? 16. And then when you add up 9 and 16, what do you get?
You get that, like 20. Sorry, I didn't do it out. 25.
Yep, 25. Okay, so we get the square root of 25, which means this vector has a length of 5. So the answer here is it's not a unit vector. It's too long. It's too long. So what am I going to scale my vector by to shorten it up to 1 unit? 1 over 5. So the answer here is going to be 3/5 I minus 4/5 j. Scaling something by 1 over 5 basically means just dividing each part of it by 5. That's all. So divide the horizontal by 5, 3/5. Divide the vertical by 5, negative 4/5. So you didn't alter the direction at all. It still points exactly the same way. It's just shorter than the original. It's basically like this picture right here. That's all we did. Okay. Any questions on that one? All right. So the last 2 things we're going to look at are the applications. The first one is easier than the second. Definitely. We'll start with that one. So first one we're going to look at is going to help us to come up with the formula for what's called a velocity vector. A velocity vector just basically represents you throwing something. When you throw something, it has a certain angle you throw it at, and it has a certain speed that you throw it at. If you tell me the angle and the speed that you throw something at, that's enough information to describe it. That's all I need to know. And when I say describe it, we're going to write a velocity vector. So we're going to write. So imagine that, just to keep it simple, because gravity complicates things, but pretend we're in like outer space and we throw something like this along this path that you see right here. What direction is that object traveling in? You have to describe it. Which way is it going? North and east, so up and right. Okay, the point is he said 2 things because it's going in 2 directions. It's not just going right, it's not just going up, it's going up and right. And if it was in outer space without gravity, not near any planets or anything, it would just keep going that way. There'd be nothing to change its course. On Earth, it would kind of curve back down. Okay? But it's going up and it's going right. So 2 directions. What I want to do is break that into a triangle. Just like this. The part that I'm going to draw in red CJ called it east, I'm going to call it right, is the horizontal. It's the right part of the vector. Could be right, it could be left. In this case, it's right. The part that he called north, I'm going to call the vertical. Take the red and the green vector and add them together, and you've just created the black one. Okay? So that black vector is made up of that and that combined together. Those are what we call the components of the vector, the horizontal and the vertical. Okay. So I told you that they would have to give you a piece of information. The piece of information that they'll give you is they're going to tell you the angle that you threw the object at, whether that the machine launched it or whatever. They'll give you that angle. Now, I'm going to label the red and the green side, but we're not going to need these labels in a minute, but we need them right now. What letter do we usually use when we label horizontal? Yeah. So let's just call this red one X. Again, you're not going to need that in a minute. And what letter do we usually use for the vertical? Y. Okay. Now, what were the two directions we just said that this was traveling in? Yep, it's going right, it's going up. So there are two parts to the vector. There's the horizontal part. So yeah, horizontal part plus the vertical part. Now, our job is to describe the horizontal and the vertical part in terms of the angle that we throw the vector at and the speed that we throw the vector at. Okay? So, what letter do we always put with the horizontal part so that we know it's the horizontal? Think in terms of vectors. I. So we're going to have something in this box with an I plus something in this box with a what? With a J. Okay. What's going to go in this box is basically the X part. Don't put X in the box because we don't want X in the box. But it's going to be the X part. That's going to be the Y part. Now we're going to break down that triangle using sine and cosine. And that's what's going to go in these two boxes. So let's start with the X. That, and that. X is what side in this triangle compared to alpha? Opposite, adjacent, or hypotenuse? Okay. It's adjacent. The V is which side? That's your hypotenuse. Which trig function has adjacent and hypotenuse in it?
Cosine.
Cosine. That's what we went over right at the beginning, cosine. So, the cosine of my angle equals adjacent over, what did we just say? Adjacent over what? What about the hypotenuse? Color of the hypotenuse, the weight of the hypotenuse, the length of the hypotenuse. The length of the hypotenuse. So you have to put those double bars around it because this symbol right here, the V with an arrow above it, that means a picture. A V with an arrow above it is that physical object. I don't want to divide by a physical object. I want to divide by the length of that object. It doesn't make sense to divide by an arrow. The length of the arrow, that makes sense. Okay. And now let's get X by itself. So how would I move this magnitude over to the other side?
Multiply.
Yeah, multiply. Multiply by the magnitude. Multiply by the magnitude. That's gone. And here's your formula for X. Magnitude of V, which is the speed you throw the object at, times the cosine of alpha. Magnitude V plus U, cosine alpha. You'll be given the speed you throw the object at you'll be given the angle you throw the object at. You just have to put those two things into your calculator and get the answer. All right. Now, let's look at the angle, the other side, and the v. So we know the v is hypotenuse. We just said that. What about y? What side is that? Yes. Opposite. So which trig function has opposite and hypotenuse in it? Sine. Sine of alpha equals opposite over, what about the hypotenuse? It's length, magnitude v. So it turns out it's pretty much exactly the same equation we had up above in terms of how to solve it. Multiply each side by magnitude of v. So this is magnitude v sine alpha. And that is the formula for a velocity vector. Magnitude v cosine alpha I plus magnitude v sine alpha j. I don't write boxes when I write this out. So we're going to leave the boxes off. All right. And if, just in case you forget, wait, what's alpha and what's that again? I wrote them right there for you. Alpha is the angle that the object is thrown at. V, well actually I should write it like this, is the initial velocity. But you have to be given those two things. This problem doesn't work if you're not given that. Speed, angle. Those are the two things you will always be given. Anyone else that needs to copy that formula down? Yeah. So the first part is the horizontal component. The second part is your vertical component. Just think about it. Very rarely would you throw something like in baseball or basketball or pretty much any sport where you hit any object or throw any object. It pretty much never goes in a perfectly straight line. Even like a line drive when you hit it in baseball. It still goes up just a little bit. But when somebody throws the ball in from the outfield, they don't throw it perfectly straight. They probably throw it up a little. I mean, they don't throw it way up, but they throw a little bit up because then it kind of helps it go further. If they just threw it perfectly straight and it never went higher than, say, like their chest, then the ball would hit the ground sooner than they want. So they throw it up a little, up and forward. In basketball, when you shoot the ball, it's up and forward. It's not just up. Just go up and hit you in the head. It goes up and it goes forward. So pretty much everything always has two components. Unless you really did, like maybe you had a model rocket and you shot it straight up and there was no wind at all and it stayed perfectly straight up and it came perfectly straight down. Then there would be no horizontal. Most of the time that doesn't happen. Okay. So it says that we're throwing an object at 50 miles per hour at an angle of 30 degrees. It says find the velocity vector and write the answer in unit vector form. Unit vector is exactly what I gave you. Something with an I, something with a J. All right. So, somebody remind me first, what is my formula for a velocity vector? I need the whole thing. Yeah.
Magnitude of v cosine alpha I plus magnitude of v sine alpha j.
Yep. Remember, what you're really doing right there is you are describing two sides of a triangle. The I part is your base. The J part is your height. That's what you're doing. Right. Now we have to fill in the four spots. Colin, what am I going to fill in for magnitude of V?
30.
What is that magnitude of v again?
50.
Its magnitude is speed. It's the velocity. So velocity in this problem is 50 miles per hour. So 50 cosine. And what am I filling in? Sarah, what am I filling in for my angle? 30. So we're going to do that out. 50 cosine 30 is the horizontal. 50 sine 30 is the vertical. So let's see what we get. First of all, we're in degrees, so make sure on your calculator you put it in degrees. And type in 50 cosine 30. So 43.3. What that means is if you were throwing this object and it was going to hit a wall, it would hit the wall at 43.3 miles an hour. You might say, well, why doesn't it hit it at 50? Well, you didn't throw it straight. Part of the energy of you throwing the ball went into fighting gravity. You threw it up. So if you had just thrown it perfectly straight, it would hit the wall at 50 miles an hour. But you threw it up and straight. So it's going to hit the wall at 43.3 miles an hour. Plus, now the vertical is basically the speed of the ball the second it leaves your hand, going up. So like if there was a helicopter above you throwing the ball, and they took a radar gun, and the second the ball left your hand, took the speed of it, that's about what we're going to get. That vertical speed changes the whole time though, because eventually as the ball goes up, it stops going up, and then it starts to go down. So the vertical speed changes the whole time because of gravity. The horizontal speed doesn't. It's always 43.3. The only way that could change is if there was wind, and it blew the ball like back towards you. Right? Something like air, that could slow it down. But if you ignore air resistance, this number never changes in the problem. And assuming no other object gets in the way and knocks the ball down. But, so let's find the vertical speed the second that the ball leaves your hand. So it's 50 sine 30. So it's 25 miles per hour. And that speed will do nothing but decrease until it reaches its highest point. And then it's going to start coming back down. So that's the velocity vector. Now, what we've basically done there is we've modeled an object that just keeps going straight forever, never comes back. So that would be like outer space, no gravity. But on Earth, that would be different a little bit because it would come back. So. Any questions on that? All right. So last example. All right. So the last example we're going to look at has to do with an object being in what's called static equilibrium. Static means that it's not moving versus dynamic. Dynamic means motion. So static, not moving. Equilibrium means balanced. Basically, in terms of physics, if something is balanced, it means that the forces acting on it are zero. This book is in static equilibrium. It's not moving. It still has weight. It's not like it's weightless now. It has weight, so it's trying to fall, but it can't fall because there's something pushing it against it to hold it up, the table. So there is a force pulling it down, but there is also a force in this table holding it up. Okay? So that's the idea of static equilibrium. All the forces are balanced. So what we're going to do is we're going to find the tension of two cables holding something up. Okay. And the idea is two cables look something like that. Now, first thing to understand is that you can have more tension in a cable than the object weighs. Easily. Think about like a rope for tug of war. Those ropes are really thick. Maybe it weighs 50 pounds, the whole rope. Pretty heavy. If you put 50 people on one side pulling, 50 people on the other side pulling, even though the rope only weighs 50 pounds, you might have thousands of pounds of tension in that rope because there's so many people pulling on it. So the tension is not just affected by how much weight is hanging from it, but also are the cables pulling against each other a little bit, like in a tug of war, or like this. The cables are pulling against each other. Now, the reason we know they're pulling each other is because what would happen if you cut that cable right there? What would happen to the weight? Yeah.
It would shift, right?
It would swing to the right. It wouldn't fall. But if you cut that cable, it would swing to the right. Well, if cutting that cable means it would swing to the right, then that cable must be pulling to the left to be preventing that. Right? Same thing here. If you cut this cable, it would swing to the left. That means that that cable must be pulling to the right to prevent it from swinging to the left. So each of these cables is pulling in two directions. Let's call this T1 for the tension in cable 1 and T2 for the tension in cable 2. Cable 1 is pulling up and it's pulling left. It's kind of like throwing the object when we threw something. It's two directions, up and left. How about cable 2? What directions is that pulling? Up and right. Okay. So the first thing we want to write down is it's more conceptual. It's just the idea of what's happening here. If this object is not moving left and right, then what does that mean about the force pulling it left and the force pulling it right? If it's not moving at all. Yeah. Which means the forces are equal. So the force pulling left is equal to the force pulling right. It has to be. If it wasn't, it would be swinging. Now, what other two forces must be equal here besides it moving left and right? Olivia?
Up and down.
Up and down. The force pulling it up is equal to the force pulling it down. If the force down was greater, it would be falling. Okay. So that's our first step. There's no numbers in there, that's just more conceptual. But that's the idea of what we're going to do. And this is where our system of equations is going to come from. Two equations. Thing is, we got to get numbers in this. These are ideas, these are just concepts. Right? I need to draw a triangle, so I need a little more space here. Okay. What I'm going to do is pretty much the same thing we did with the velocity problem. I'm going to break the force into its two directions. The up part and the left part. Or in case of the one on the right, the up part and the right part. So we're just making triangles out of all that. Okay. Now, visually, for cable 1, that represents the force pulling left. That represents the force pulling right. That's cable 2. Back to cable 1. That represents the force pulling up. For cable 2, that's the force pulling up. So there's really 4 vectors involved here. A left, a right, an up, and an up. So, what letters do we usually use again when we label horizontals? Yeah?
I.
Okay, so yes, for the vector, we use I. How about like when we do like an axis? Yeah, so let's stick with, let's call this x1. Let's call this one over here in red x2. Okay. What do you think I'm going to call the green one on the left? Y1, because it's a vertical force. Y1. I mean, why am I using the subscript 1? Because I use the subscript 1 for the x. That's all. And what about the green one on the right? Y2. So now we're starting to get we're going to start to get a little bit less conceptual and kind of start to get some labels in our formula. So I'm going to translate this now into x1s and y1s. What did we use for a label that represented the force that's pulling left? x1. x1 is the label for the force pulling left. How about Delise? What's the force pulling right? Yep, x2. So x1 equals x2. And Colin, what's the force pulling up? Yeah, y1 and y2. They're both working together. That's why if you cut one of these cables, it wouldn't fall, because there's two forces holding it up. y1 and y2. And we already know the force pulling down. What's the force pulling down in this problem? Yeah, 1,200 pounds. That's the only thing we have a number for at the moment. Okay. So that's step 2 in terms of your equations. So you're starting to take it and get more numbers involved rather than just conceptual. You can start every problem off like box 1. Force left, force right, force up, force down. But then you have to start to get more of the specifics of the problem. Now, we're going to want to substitute for 4 things. x1, x2, y1, y2. You might start to see a pattern. If not, I'm going to do the same thing 4 times. But I want to start to get sines and cosines and angles in this now. The specific angles from my problem. So, let's start with this angle right here. How much is that angle at the top of the left triangle? Yeah, 60. So how much is the angle down here in the bottom? 30. Right. How much is this angle down here at the bottom? Yeah, it's a 45. Now we're ready to start doing sines and cosines. Before we wrote that, we didn't have any angles in these 2 triangles. We had angles outside the triangles. Okay. But now we've got 2 angles inside. Right. So now we'll start with the same thing. We'll have to do 4 times if we don't start to see a pattern, but hopefully, maybe we will. We got this, this, and that. x1, is that opposite, adjacent, or hypotenuse? It's adjacent. And Matthias, what about T1? It's the hypotenuse. Okay. So CJ, what trig function has adjacent and hypotenuse in it?
Cosine.
Cosine. Yep. So off to the side, I'm going to write down cosine of my angle equals adjacent over hypotenuse, x1 over t1. Now, my goal is to get a formula that I can plug in for t1, x1. So how would I get t1 on the other side?
Multiply.
Yeah, multiply by t1. Multiply by t1. There is your formula for x1. T1 cosine 30. Right, let's do y1. So now, I'm just going to move these circles off. We're going to focus on y1, t1, and that angle. Carolina, what side is y1? From the perspective of the 30. It's opposite. And Jacob, what about T1? Hypotenuse. What trig function has opposite and hypotenuse in it? That's adjacent hypotenuse. Sine. So sine of 30 equals opposite over hypotenuse. Y1 over T1. Y1 is opposite, T1 is hypotenuse. Now, how would I get Y1 by itself?
Multiply both sides by T1.
Multiply both sides by T1 times T1. There's your formula for Y1. So now we have X1 and we have Y1. Now, we can do this 2 more times or we can try to notice the pattern. When you're dealing with the X values, cosine is the function that's involved. When you're dealing with Y's, sine is the function that's involved. The sine is always the up and down. Those are your Y's. Cosine is the horizontal. And that's your X. So, anybody think they could tell me what X2 would be? It's going to be kind of like one of the boxes we have up above it. Yeah?
T2 cosine 45 degrees.
Exactly. T2 cosine 45. And when I'm doing a problem like this, honestly, I pretty much skip step 1. I skip step 2. I go right to the 3rd step. And I just look at the picture and I say, okay, all the x's are going to have cosines. What's the angle? Oh, 30. All the y's are going to have sines. What's the angle? Right? And I look at, 45. It depends on which triangle you're doing. 2 of them are going to be 30s. 2 of them are going to be 45s. Right. So how about y2? Anyone think they can tell me what y2 is? DJ?
T2 sine 45 degrees.
Yep. It's a 2 because that's a 2. All the 2's are together. 1, 1, 1, 1, 2, 2, 2, 2. The subscript stays the same. That's how you can remember what goes with what. T2, he said sine, because sine is always used for the up and down. And now look at the angle in the problem with the T2. It's 45. All right, so now step 3 is to set up the actual equations that we can plug into the calculator and get the answer. And this is the step that I usually jump right to. But if I just jumped right to this step without doing the first 2, you would have no idea, like, where did he get the first equation from? It's because force left equals force right. That's where I got it from. Okay. So, force left equals force right. Force left is x1. T1 cosine 30. Force right is x2. T2 cosine 45. That's the first one. Second equation, force up equals force down. The force up, there's 2 cables pulling up. Y1, which is T1 sine 30, plus Y2, that's the other cable that's helping to pull up. T2 sine 45. And those 2 cables are supporting a weight of 1,200 pounds. Okay. Now, the last step I'm going to do, we're not going to solve it today. We'll finish solving it during the homework. I'm just going to change everything here to decimals. I'm going to plug all those numbers in on my calculator. All right, cosine of 30 is 0.866 equals cosine of 45. I already know that one. common one, 0.707. Sine of 30 is, if you type that in, 0.5. 0.5 T1 plus sine of 45. Again, I know that one too because it's common. It's 0.707. Yes, it is the same as the one above it. Equals 1200. All right. And now, what you have right there is basically something like 3x equals 2y, 5x plus 3y equals 12. Just change the t1 and t2 to an x and a y. Now you have a system of equations to solve. Right? And from there, we'll use substitution to finish it. So, yeah, it's definitely an involved problem. But once you know the pattern, you don't have to go through step 1 and step 2 every single time. You can jump right to step 3. The first time or two, you probably want to go through the steps because you might get confused. But if you did like 4 or 5 of these in a row, guarantee you by the time you get to the 5th or 6th problem, you'd be jumping right to step 3. As long as you keep your work organized. If your work's kind of all over the place, then you kind of get lost. That's why I try to do boxes and keep it nice and neat. Okay? So I'm going to save that, and we'll come back to finishing that up in the homework. You probably need another 2 minutes to finish that up. And we'll do that when we go over the homework. So on the homework tonight, there is a question like this. All you really have to do is if you look at step 3, change this angle to the one they give you in the problem, change this angle to the one they give you in the problem, and change this number to the weight they give you. Now that you know how to do those 2 equations, that's all you'd have to do every time. Just change the angles and change the weight. And you can jump right to step 3 without going through all the steps. Okay. So only try to get this far on the one in the homework. If you want to finish it, you can, but you don't have to. We'll finish it together. Okay. So the homework, that's 25 to 47 odd. And then 55, 57, and 66 is obviously even. All right, so we'll take a look at that. Don't forget, if there is anything that you need to make up, make sure you come talk to me and get that done by Friday.